Hello everyone, here's another IB Physics past paper review. This is question 3 of May 2018 standard level paper 2. And here we have a beam of coherent monochromatic light. Doesn't really matter where it's coming from, and it's being used to with some optics experiments. So we've got this parallel beam being incident on a double slit, so that's just referring to these directions of rays. They're perpendicular to the double slit, and so they're coming in. The wave front, if you like, is passing through the double slits, and we're getting this interference pattern. We have a gap between the slits of 0.3 millimeters. And the screen with which we're able to see this interference pattern is at a distance d from the double slits, or from the slits. And we've got a diffraction angle. So obviously we're going to be using some calculations to get some values, but I wanted to just spend a little bit of time here on part 1, or part 1, where we have to do a little qualitative analysis. So it's just saying that, the observation would obviously be, and hopefully you've all seen this in the class, you're going to get a series of bright fringes, but you're also going to get a series of dark fringes. And what that looks like in the classroom or the lab is just the absence of light. So it may not, when we see the word dark, obviously it's not creating a shadow, but it's just the absence of light. So we have these dark, bright, dark, bright, dark, bright, repeating pattern. That's the interference pattern, and we call them fringes appearing on the screen. So we need to explain how a dark fringe is formed. We often focus a little bit too much maybe on the bright spots, because that's what we can see, but forgetting that in the middle of these bright spots would be the absence of light. So here's our normal sort of experimental setup. We've got the central maxima that I've drawn on here, and then the first bright spot here, and then there's the angle in there. So I just wanted to spend just a quick recap on the explanation as to why there is a dark fringe, and it's to do with, of course, constructive deconstructive interference. So let's just see if we can zoom in a little bit and take a look at these waves that I've drawn onto the double slit here, and you've probably seen this before. So these are the two gaps, the two slits, or part of the diffraction grating, and the light is going to be bent as it moves through. There's going to be a change in direction, and what we're looking at here is just a part or a representation of the wavelength of the light traveling in the direction that we see here, this theta angle. And so you can get some of it coming from this slit and some of it coming from this slit. What we're interested in is the wavelength of light represented by this blue triangle here. So let's see if we can show that. Now, I've tried to do this as best I can. So there's this blue line here. This blue line here would now represent the wavefront moving this way, and hopefully you can see that I've tried to draw the wave at a particular phase of its cycle, and they match. So this phase of the wave here matches with this phase of the wave here as they move as a wavefront this way. And so you can see from this diagram that these wave phases are in phase, and we're going to get constructive interference. Now that explains why, if we keep following this direction, we're going to get the bright spot, because remember, we're going to get a bright spot when we have this constructive interference. So that's what we're going to see here. If we were to do a little algebra on it, we could put the angle, this angle here is going to be the same as this angle here. And let's call this part of the triangle S. And then, of course, this gap we're going to call D. So just using trigonometry here, we can see, hopefully, that S over D, let's just put this here, S over D is going to be equal to sine theta. And that's for when S is equal to a wavelength. So let's just put that in parentheses. When S is equal to a wavelength. Or more formally, perhaps, when S is equal to some integer of a wavelength. So this would be for bright lines. This is going to give us constructive interference, and this is going to be bright. Okay, but what about the dark lines? Because that's what this question is asking about. What about when things are dark? Well, if I redraw my my wavelengths, and now I'm going to put half a wavelength into this part of the triangle. So now I'm saying that half a wavelength is S. If we match these wavelengths up, you can see that the phase of this wavelength is just about to come down, and the phase of this wavelength is just about to go up. So they are completely out of phase with each other. So they're going to produce deconstructive interference. Take a look here. This is the trough of a wave, and this is the peak of a wave. They're going to completely cancel each other out and give you no light. That's what gives us this dark line. So we can now make a statement about that as well. We can say that we're going to have half a wavelength at, let's just say at S. So S is half a wavelength, and that's out of phase. Out of phase completely. And that means that when we have deconstructive, the S is going to be wavelength over 2. Or more formally, as we'd previously put, let's just put it down here, we're going to say 2n minus 1. Let's put that in brackets. 2n minus 1 wavelength over half. So that's an integer value. 2n minus the 1 wavelengths divided by 2. We could simplify that as we have, as we can see in our data sheet right here. So this is on your data sheet, so there's no need to memorize this. We're going to simplify it as n plus the half wavelength. Basically, when you have half a wavelength fitting into this S part of the triangle, you're going to have completely deconstructive interference. That's going to give you the dark lines. So to wrap up the question qualitatively, we're going to say sort of 3 main points. First of all, the obvious one, we're getting interference of light from both slits. So here are the 2 slits, light's going through both of them, and the light itself, the wavelength of the light, is interfering. So that's key. The second point is the algebra bit that we just stated. We summarized it down to n plus a half times the wavelength. This is on your data sheet. You don't have to memorize this. The key bit you do have to memorize is that the n value, the integer values, have to be odd. That makes sense when you're thinking about this, the number of wavelengths in here. This is half, so it's 1 over 2. So 1 over 2. You could have 3 over 2, or 5 over 2, or 7 over 2. It doesn't matter. It has to be an odd number. That's where this piece came in, 2n. So 2n minus 1 is going to give you that odd number. And then the last one is just that the interference would have to be deconstructive, and that's going to give you the no light. Okay, so for part 2, now we're just doing a calculation. We're given our situation here, which is our diffraction grating information. We know the little d here, the distance between the slits, is 0.3 millimeters. We're then told that the wavelength of this beam of light is 633 nanometers, and the separation between a dark and a bright fringe is 4.5 millimeters. And that's actually an important little detail, because our formulas, if you recall, our formulas are actually coming from the idea that this triangle is from the central maxima, this one here, to this n equals 1. These are both bright lines, so these are bright and bright. Of course, the dark would be in the middle, so this would be a dark spot here. So this gap here between the central maxima and n1, this is the S value, but we're not given the S value. Really, we're given the S value divided by 2. So S divided by 2 is 4.5 millimeters. Because, of course, we're halfway between the two bright lines, or at least that's the assumption in this question. So S is between the two bright lines, but we're given a value that is halfway. So I'm dividing this S value by 2. That's the 4.5 given. So, of course, our true S value would be 9 millimeters. Okay, and that's really important. The other thing we need to check is our angle. We always need to check that our angle is less than 10 degrees. If it's less than 10 degrees, we're okay to use our small angle approximation, at which point we're able to use this equation given on our data sheet. Remember that this equation here is given, is only valid if the angle is less than 10, because it treats this angle, this triangle, as tan theta being equal to sine theta if this angle is less than 10 degrees. So let's go ahead and just check that. We're going to check the angle for small angle approximation. So we can say that, well, let's just state our two formulas that we can use to find the wavelength. So we have our datasheet version, which is ds over capital D. And we can also say, so this would be based on our small angle approximation. We can also say, taken from the original derivation, that if we use, what am I doing? I wanted to put d sine theta over the number of n values here. And actually I should put the number of n values in there as well, even though in this case we're only dealing with 1, so we would ignore the n, but doesn't matter, we'll put it in anyway. These are the two formulas. So if small angle approximation is true, I can use this. If small angle approximation is not true, then I have to use this. So let's go ahead and just solve for this angle, and that's going to give us an idea about whether or not we can go ahead and just use the S value that we have and the wavelength value that we have to find D. Okay, so let's do that. Let's find the angle. So the angle is going to be, just rearranging our equations here. We go lambda over S, lambda over D, and then inverse sine. So that's going to give us an angle of, plug that into your calculator, 0.0012 degrees. Okay, we're good. Small angle approximation is good to go. So we're able to use this equation here to find the capital D, the length of the distance away of the screen. So D, therefore, is going to be, ds over lambda. And if you plug that in, you're going to get 4.27 meters. Checking for significant digits, I need to use 3. I've got 3, and we're good. Okay, so part B, interesting scenario here. That's why in the original question it did say on the surface of Earth. So the diffraction grating was then, we're assuming that it's air that the light is traveling through, which has a refractive index of essentially 1. Now we're changing out that air for water. So the light as it passes through the diffraction grating, then travels through water before it is incident on the screen. And of course, when wavelengths move through water, there's a change in their behavior because they're traveling through a medium. And that is indicated by Snell's law, which gives us these refractive index ratios compared to the angle ratios, the speed ratios, and hopefully you can also recall, which is really important for this question, there's also a wavelength ratio. So in this case, lambda 2 over lambda 1. Now, what we're looking at in our question is air and water. We're going to be comparing those things because we know some information about the light and the wavelengths in air. What we're now going to do is try to find the wavelength in water. So let's just go ahead and say that we've got the wavelength in air, and if we use Snell's law, that's going to be equal to the wavelength in over the wavelength in water. And now we can look at the refractive indexes. So we're going to put the refractive index of water and the refractive index of air. So we should know that the refractive index of air is 1. We're told in the question that the refractive index is 1.33, and we're told in the previous part of the question that the wavelength in this question of the in the air is 633 nanometers. So we know those three things. So clearly this is pretty straightforward now. We're just rearranging Snell's law and solving for the wavelength in water. So let's go ahead and just do that. We'll plug in our numbers. We're going to say the wavelength in water is equal to the refractive index of air times the wavelength in air divided by the refractive index in water. And so plug in those numbers in, you get 1, that's the refractive index of air, and then you get your 633 nanometers. That's the wavelength of the light in this situation, in air, and then your refractive index of water. And that gives you 476 nanometers to 3 significant digits. And that makes sense because the speed, of course, in water, so this V2 is going to be decreased. Speed of light decreases in water, and therefore if V2 decreases, lambda 2 should also decrease. And that's exactly what happens. It goes from 633 nanometers, so red light, down to 476 nanometers, which would be closer to blue. Okay, so part 2 here of part B of question 3. Just to finish things up, we are talking qualitatively now about what we would expect to see on the screen as a result of changes in the intensity because of this change in refractive index. So in part 1 there, we'd worked out that the wavelength was going to decrease. So the wavelength is going to decrease. So the wavelength in water is smaller than the wavelength in air. So the wavelength in air is bigger. Actually, we'll put this as a proportion. Okay. So let's look at our formula, first of all, over here. This was our diffraction formula. What we're saying is that the wavelength has decreased. So if we keep capital D is the same, that's the length between the screen, and the screen spacing is the same. So what we're looking at here is the proportionality between the distance between the bright images and the wavelength. And since the wavelength has decreased, we would therefore expect the spaces between the bright spots to also decrease. So that would be one observation we would expect. So we can state that as the distance between the peaks is going to decrease. So distance between peaks, or I'm going to put in brackets, bright fringes, decreases. The other thing to think about is when a wave is traveling through a more dense medium, obviously the wave is affected. And in Snell's law, we see that if N2 is water, it has an increased density. If this goes up, the density goes up, then the speed has to decrease. There's an inverse relationship. And so we can say the same thing about the amplitude. In other words, the amplitude of a wave, so we'll call this amplitude of the wavelength, that's going to decrease. That's going to decrease in a refractive index that is bigger. Okay, so what we're saying here is that as the density goes up, as the refractive index goes up, the amplitude of the wavelength is going to drop. And the other bit of information on our data sheet here is that there's a relationship between the amplitude of a wave and the intensity. And so the amplitude squared is equal to the energy or the intensity of a wave. And so if the amplitude decreases, what's going to happen to the intensity or the brightness? It's also going to decrease. So we would say the amplitude is going to decrease. Therefore, the brightness, we'll call it the intensity of the bright fringes decreases.